In the last class, we have already discussed about allocation of frames. As I said to you earlier, each and every process is divided into pages. The pages need to be in the main memory frames for the execution, right? So each and every process allocated some frames. How many number of frames we need to allocate to the process? Okay, there are two types of techniques. One is under the fixed allocation, there are two types of techniques. What are those? Equal allocation and proportional allocation. In the case of equal allocation, each and every process will get the same number of frames, whether the process is a big process or whether the process is a small process. All the processes, the frames are equally shareable to all the process. That is about equal allocation. In this example, for example, there are 100 frames and the number of process in a machine are 5. So each process will get 20 frames. 20 into 5 is 100, right? So that is called as equal allocation. And the second one is a proportional allocation. So what is the need of going to the proportional allocation? So if a process is small, for small process, you are allocating 20 frames. Even if the process is big also, you are allocating the same number of frames. So it is always better to provide the frames to a process based upon the process size. It is always better to allocate frames based upon the process size. Why? Because if the process size is small, you are allocating 20 frames to the particular process, for example, and one more process is there, you are allocating 20 frames even for that second process, big process. The big process requires more number of frames, but you are allocating 20. The small process does not require 20 frames, but because of the equal allocation, you are allocating 20 frames to the small process also. So what happened then? The small process memory frames will be wasted, and then the big process requires more number of frames, but they are not available to that particular process. So that is the problem with equal allocation. In order to avoid such situation, we will move to the proportional allocation. So proportional allocation means proportional to the size of the process, we are allocating frames. So this is the formula. SI means size of a process, PI, and capital S is sum of the sizes of all the process in a machine. M means total number of frames available in a machine. And next AI means allocation for PI. So for example, this is the formula. For example, M here is 64. S1 means size of process 1. Here we have two processes. The first process size is 10 KB. Maybe the second process size is 127 KB. How can we calculate? So we need to use this formula, right? For AI means here A1. For process 1, how many number of frames we need to allocate? A1 equal to size of the process by total process. SI means size of a particular process by total size. So what is the size of the process? 10. S1 is 10, right? And what is the total size? 10 plus 27. Total size means 137 into number of frames 64. So 10 by 137 into 64 and approximately 5. Then what about A2? A2 means allocation of frames to the second process. So size of the process by total size. What is the size of second process? 127. Follow the cursor. The size of the second process is 127. So 127 by what is the total size? 10 plus 127, 137 into total number of frames, M, 64. So approximately 59. That means the small size process P1 will get 5 frames and the big size process P2 will get 59 frames. That is called as proportional allocation. And the next one is a priority allocation. So what is priority allocation? The high priority process will get the more number of frames when compared to the low priority process. That is called as priority allocation. As the name indicates, you need to allocate a more number of frames to the high priority process when compared to the least priority process. And the next one is a global versus local allocation. What is global allocation and what is local allocation? In the case of global allocation, the process can select the frames from the other process frame. The process can select the frames which were allocated to the some other process. For example, in a machine, there are 4 number of processes, P1, P2, P3, P4. So the P1 can access the frames, the P1 can use the frames which are allocated to the some other frames. That is called as global. Okay. There is a security issue with the global, and the control also very difficult. Why? Because which process are using which frames, there will be no control if we are allow the global allocation. And the next one is a local replacement. What is local one? Observe the line. Each and every process selects from only its own set of allocated frames. That means the process is allowed to use the frames which were allocated to it only. It should not use the frames which were allocated to some other process. Whereas in the case of global replacement, what happened? So if a process needs some frames, the whatever the frames allocated to that particular process are not enough. For example, it requires some more frames to complete its task. So what it will do? The process can take the frames from the set of all frames which are already allocated to the some other process. Okay, that is the thing. Follow the cursor. One process can take a frame from another process. That is about global. One process selects a frame only from its own set of allocated frames. That is called as local. Okay. And now we are going to discuss about thrashing. So what is thrashing? So thrashing means high paging activity. Thrashing means high paging activity. So what is high paging activity? So let me explain you with the help of paint. Sorry. Carefully listen, very important concept it is. Thrashing. So what is thrashing? I already told you, high pacing activity is called as thrashing. Thrashing, right? So what is the problem, right? So what is this high pacing activity? So for example, whenever you want to execute the program in the uniprocessor system, what you did? The entire main memory is divided into two parts. One is for the operating system and the entire remaining area is for user programs. This is the user area, the entire memory, right? So whenever user want to execute a program, that particular process need to be kept in the main memory for the execution. If it is a single user operating system, what happened? There is only one process. There is only one process in a main memory at a time. So what is the problem if you only keep one process into the main memory? So whenever there is a process waiting in the main memory, operating system allocate CPU to this particular process. Okay. For example, CPU is now executing the P1. Suddenly, process 1 requires a read operation. Okay, where the process need to read the information. Read means from a file. Where the file is available, the file might be available in the disk. That means it is a disk read operation. Disk is a secondary memory and CPU is the fastest device. Whenever the process is reading the information from a secondary memory disk, at that time CPU will become idle, right? At that time CPU become idle. So what happened if the CPU become idle? Automatically, when the CPU will become idle, so the number of processes executing per second or number of processes executed per unit time will be less. That is called as throughput will be reduced. Whenever the throughput will be reduced, automatically system performance will be reduced. Okay. How can we overcome this particular problem? In order to keep the throughput high, what you need to do? The cpu need to busy all the time. The cpu need to busy all the time. Okay. So how can we keep the CPU busy? We need to keep the CPU busy. Now whenever we CPU executing the P1, so P1 process 1 requires a read operation from a disk. At that time CPU will become idle. So we should not keep the CPU idle. So how can we make it busy? So we need to allocate the another process to CPU. We need to allocate another process to CPU. Meanwhile, P1 is executing the read operation. Okay. So because of that reason, we should not keep only one process into the main memory. How can we solve this particular problem? With the help of multi-programming. With the help of multi-programming, what we can do? We can keep multiple programs into the main memory. Rather than a single process like P1, you keep multiple programs into main memory. Okay, if you keep multiple programs into the main memory, so what happened? For example, earlier there is only one process P1 in the main memory. Now you can keep multiple number of programs into the main memory with the help of multi-programming. Okay, earlier it was single user operating system, only one process is available in the main memory. But with that we have a problem like CPU idleness. In order to avoid such a situation, we will move to the multi-programming. What is multi-programming? Keeping the multiple number of programs into the main memory. So likewise, if the P1 is busy with the read operation, then automatically CPU switched to some other process. Okay, the CPU switched to some other process from P1. Okay, why? Because now in the main memory you have another process. For example, P2 is also busy doing with some IO operation. So CPU can be switched to some other process. Likewise, CPU has always a process to execute. Okay, that means whenever there is a disk operation or a read operation or IO operation, or the particular process suspended or interrupted for any of the hardware issue, so automatically CPU can be switched from P1 to P2. We can switch the CPU from P1 to P2. So how can we switch the CPU from P1 to P2? Because now in the main memory, we have more number of programs, not only one program or one process in the main memory. Right? This concept is called as multi-programming. So if we keep more number of programs into the main memory, if we keep more number of programs into the main memory, what happened? Initially, system performance will be more. If you keep on increasing the process into the main memory, what you think that if you keep more number of programs into the main memory, so that CPU is always busy. If the CPU is busy, automatically system performance will be the more. So this is the concept. So what you will do in order to increase the system performance, in order to make the CPU busy, what operating system will do? Operating system initially encourage the multi-programming and keep more number of programs, keep on increasing the more number of process into the main memory. Okay, so what happened? If you increase the number of process into the main memory, and if you are allowed more number of programs into the main memory, what happened? So initially, for example, this entire user area is of 1024 KB, for example. Initially, you kept only two processes into the main memory. So how much both the process will get? If it is an equal partition, so 1024 by 2. Why? Because we have only two processes into the main memory. So how much each process will get? 512 KB to each process. P1 will get 512 KB and P2 will get 512 KB. So what happened if you keep multiple number of programs into the main memory? Even more, you increase the size to 4. That means now you keep the 4 number of programs into the main memory. You want to keep 4 number of programs into the main memory. That means you want to increase the multi-programming. So what happened? 1024 by 4. Why? Because now we have 4 programs into the main memory. So each will get how much partition? 256 KB. Every process will get 256 KB. Likewise, if you increase the things into 1024 by 8, so automatically what will be the situation? That it will be even still reduced to some value. What is 1024 by 8? Let me know. Right, 128 KB, right? Half of the 128, right? So likewise, Likewise, if you keep on increasing if you keep on increasing the programs or process into the main memory, what happened? The size which was allocated to the individual process will be decreased. If the size is decreased, what happened? The entire process is divided into pages, right? Okay, if you allocate a small number of frames, if you allocate small number of frames, what happened? The process cannot keep all the pages into the main memory frames. Are you got my point? If you keep more number of programs into the main memory, if you keep more processes, so what happened? We can't assign more frames. Why? Because the entire memory is divided into partitions and we need to allocate to the individual process, right? So when more number of processes are in the main memory, so individual process will get the less number of partition. So it will get only few frames. The process, each and every process will get only few frames. Why? Because if there are more number of process, even if you are trying to increase the multi-programming, whenever you are trying to increase the multi-programming, you need to keep multiple number of process into the main memory. Whenever the multiple number of process are there in the main memory, automatically what happened? The frame number of frames, for number of frames for every process will be reduced. Okay, as I told you, a birthday party example. So if you invite only for two friends to your birthday party, the cake will be divided into two partition, and this is for you and this is for your friend. If you invite four members to the party, automatically you need to divide the cake into four partitions, 1 2 3 4 you can share. If you invite 8 members into the birthday party, again you need to cut them into the more number of pieces. So the partition size will be reduced if the number of people are increased. If you observe here, right? Even if you want to increase the number to 16, what happened? Again you need to divide into the multiple partitions, right? So 1 2 3 4 5 6 7 8 9 10 11 12 13 14. If we invite 14 members to the birthday party, so each and everyone will get a small piece of cake. Like that fashion, here also, if more number initial, if you for example only two people are invited to the party, the fun is less. In order to increase the fun, what you people do? You increase the number of friends. You are trying to invite the more number of your friends to the party in order to increase the fun. So what happened? Automatically the size of the cake will be reduced. So when even if you want to increase the number, so like that fashion here also, whenever you want to increase the system performance in order to make the CPU busy, initially you keep only two process. So after that, in order to increase the system performance, you want to increase the multi-programming. Again, you want to keep one more process. Again, you want to keep more process. Like that, if you increase the degree of multi-programming, that means number of process into the main memory. So automatically what happened? For every process, you can allocate, for every process you can allocate, or OS can allocate few frames. That is the problem. Few frames. Okay, frame is a part of a main memory, right? So as there are more number of process in the main memory, only you can allocate few number of frames to the individual process. So what happened? So for example, P1 requires 10 frames. Why? Because P1 is divided into 10 pages. Okay, like that P2 is divided into 15 pages. P3 is divided into 20 pages. So for with the help of equal partition, we would like to give the 10 frames. Now in the main memory there are 30 frames. What happened? So for example, for each and every process will get 10 frames. right? Why? Because the total number of frames are 30. So what you people will do, you invite some more 3 process into the main memory. You would like to increase the degree of multi-programming. This process is also of 20 size, this is of 30 pages, and this is of 25 pages, for example. So now you have only 30 frames, right? What you need to do, with the help of equal partition, you need to change this one, right? If the degree of multi-programming is more, na, automatically what these values will become? There are only 30, na? How many number of processes are there in the main memory? 6. So each process will get only 5 frames, right? If still you want to increase the multi-programming, still you want to add 3 more programs into the main memory, or you want to increase the 4 more process into the main memory. So whenever you increase the process into the main memory, automatically for each and every process we can allocate only few number of frames. Okay, for example, like that, if you invite a 10 number of process into the main memory, how many there are 10 process now, like that you are increasing up to p10. Okay, so now in the system there are 10 process. So what are the number of frames available in the main memory? 30 frames. 30 by 10 means only 3 frames per a process. If you allocate only 3 frames for a process, what happened? Whenever you want to execute the P1, how many number of pages you can keep into the main memory? Page 0, and then page 1 or page 2. Only 3 pages you can keep into the main memory. Why? Because for every process we have only 3 frames. So what is the size of P1? It is divided in 10 pages. How many frames you have given? Only 3 frames. So every time if this frame number is decreased, na, the required page is not there in the main memory. Whenever it want to try to execute P3, page 3, right? But page 3 is not there in the main memory frame. What you need to do? You need to take out any of the one page from these pages, and we need to brought in page 3. Again, now we want to execute page 4. There is no main memory, right? Free memory frame is not there for P1. Only 3 frames, right? Again, you need to keep this page and you need to take out one more page. Like that, every time there is a page fault. The page fault rate will be the more. If you keep on increasing the multi-programming, what happened? Every time the system is busy with page faults only. Okay, if it is okay for P1, what about this P5? P5 require 30 pages, but how many pages you are giving? Only 3 pages. That means only 3 pages are in the main memory. 3 pages, 3 pages you can kept in the main memory frames. The leftover 27. Why? Because 27 3 plus 3 is 30, right? So leftover 27 pages need to be kept in the reside in the secondary memory itself, right? Only 30, from 30 only you can keep 3 pages into the main memory frames. Remaining 27 will be there in the secondary memory backing store itself, right? So that is the problem. 27 pages are in the secondary memory. Automatically every time you want to execute a page, that page is in the secondary memory. So page fault occur. Whenever there is a page fault, you need to select one page from these pages out to the main memory, and you need to keep the required page into the main memory. Again there is a page fault, again there is a page fault. Every time that means it takes more time for the page fault rather than the execution. Rather than execution, every time the system is busy with the page faults. That is the problem. That is called as high paging activity. High paging activity means if the number of frames we allocated to a process is very less in number, automatically the process cannot keep multiple number of pages into the main memory. For example, if it is a 30-page process, we are allocating only 3 frames to that particular process. 27 pages are remain in the secondary memory. So whenever there is a need, that page is not there in the main memory. Page fault occur. You need to swap the one page from the main memory, and we need to swap in the required page to the main memory, right? Again page fault, again page fault. Why? Because more number of pages. Out of 30, only 3 are in the main memory. Remaining 27, majority of the pages are available in the secondary memory. So every time, whenever there is a page required, that is not in the main memory. Whenever you require a page for execution, for CPU, that page is not available. So all the time, page fault occur. That is the reason why the system performance will be reduced because of this high paging activity. Why this high paging activity happened? What is the reason? So initially, in order to improve the CPU utilization, in order to make the CPU busy, with the help of multi-programming, you are keeping some process. The CPU utilization will be more initially. So you want to increase the CPU utilization even more, the multi-program will be moved to the next level. Again, you keeping more number of programs into the main memory, even more, even more, even more. Like that, if you keep more number of process into the main memory, so automatically the number of frames which are allocated to the individual process will be reduced. So that every time there is a page fault. Okay, whenever there is a page fault, so automatically it will be a problem. The operating system is always busy with the paging activity rather than the execution, right? That is a problem. So let me explain you with the help of a diagram now. I think you have enough knowledge about thrashing. So this information is enough for you to understand. Okay. So if a process does not have enough pages, and that enough frames, sorry, not enough pages, it is wrong notation. Enough frames does not have, that means does not have enough pages into the main memory, right? Enough pages in the main memory. Required pages, or the process cannot keep the required pages into the main memory. That means it has not have enough frames. It indicates, right? The page fault rate is high. If the page fault rate is high, CPU utilization is low. Operating system thinks that it needs to increase the degree of multi-programming. Whenever the CPU utilization is low, because of multi-programming, it happened, so I want to increase the multi-programming. Another process is added to the system in order to increase the CPU utilization. If we add more process into the main memory, again the number of frames to a particular process will be the low. Okay, so likewise every time whenever there is a CPU utilization decrease in CPU utilization, the operating system will try to increase the multi-programming. Whenever the operating system try to increase the multi-programming, more number of process into the main memory. If more number of process into the main memory, the frames which are allocated to the particular process will be reduced. So it is a cycle process, right? So because of this problem, crashing happened. Okay, a process is always busy with swapping the pages in and out. That means execution time is less and swap in and swap out time is more. That is called as crashing. So this is the diagram. Whenever you are trying to increase the CPU utilization, follow the cursor please. Follow the cursor please. Whenever you are trying to increase the CPU utilization, the CPU utilization is more. From here to, it will be in the increasing direction, right? Whenever you increase the degree of multi-programming means number of programs into the main memory. So if you increase the number of programs into the main memory, initially the CPU utilization is more. So if you want to increase CPU utilization even more, to try to increase the number of programs into the main memory. Likewise, up to this point, the CPU utilization is more. So increasing in increasing direction. Whenever you even trying to increase the multi-programming, whenever you try to increase the multi-programming in this direction, automatically after some time what happened? The more number of process into the main memory, so that the CPU utilization will be reduced drastically. Why? Because from this particular point, the each and every process has allocated rest number of frames. So automatically you cannot keep more number of pages into the main memory. Okay. If you are not keeping the more number of pages of a process into the main memory, page faults are more. So automatically page fault means you need to take out one page from the main memory and you keep in the required page into the main memory. That is called as swap in and swap out. That means always the process is busy with swapping and swap out, page in and page out. Okay, that is called as thrashing. So how can we avoid the thrashing? So how can we avoid the thrashing? Let me explain you again with the paint. So why page fault happened? Why? Why page fault happened? What is a page fault? Required page is not there in the main memory. Then page fault occur. Okay, what you need to do whenever there is a page fault, you need to take the page from secondary memory and you need to keep it to the main memory, right? So that is called as page fault. Okay, so in the case of thrashing, the page fault ratio is more. So how can you avoid this situation? If you keep most free important pages into the main memory, important pages here means the pages we require all the time for the execution. At the time of execution, whatever the pages of your process, for example, in our example, the page is having 30, the process is having 30 pages, right? In those 30, how many pages do you require? How many pages you can keep into the main memory? 3 frames in our earlier example, right? So in those 30, what you need to do? So you need to select the most important pages, desired pages for the execution. So those pages you need to kept into the main memory. So whenever the important pages are there in the main memory, automatically CPU busy with executing that particular pages, right? So the most important pages for the execution at that particular moment of time. For example, this is our program, right? So in our program there is a main block and there is a module 1, that means function 1 or function 2. Like that, there are so many number of modules in our program. So which part is the most important? You need to keep that particular page into the main memory so that the page fault will be less. That is called as locality. We call it as a locality, and based upon the importance you need to keep the pages into the main memory. So how can we identify the important pages? When we are executing a particular process, at that particular moment of time, which pages are required for the CPU for the execution, those pages you need to keep into the main memory based upon the locality, right? That is the thing. For example, if you observe this particular reference table, delta at a time t1, what is the working set? Working set. Here we have a more number of pages from 2 to 7, right? In those 2 to 7, which pages are much needed for you? At the time t1, 1, 2, 5, 6 and 7. Follow the cursor. 1, 2, 5, 6 and 7. These pages are required for the process at a time t1. So 1, 2, 5, 6, 7 pages are need to be there in the main memory at a time t1. For example, at a time t2, what are the pages do you require? At a time t2, time t2 is start from here and end it here. So only 3, 4 pages are required, that when the CPU executing that particular process at a time t2, we require only 3 and 4 pages. At that time, how many pages we need to keep into the main memory? At that time, it require only 3, 4 pages. If we keep 3, 4 pages into the main memory, so automatically there will be a no page fault. Why? Because the required pages are already there in the main memory, right? For example, from 1 to it last 4, it may be the time t3. At a time t3, what are the pages do you require? 1, 3, 2, 3, 4, 4, 4, 3, 4, 4, 4. That means we require only 1, 2, 3, 4. Only those 4 pages are in the working set. Likewise, at that particular moment of time, T1 or T2 or T3, at that particular moment of time, what are the pages the CPU required? Those pages you need to keep into the main memory. So that is called as a working set. If you keep that pages in the main memory already, then CPU does not require some other pages, right? Already the required pages are there at that particular moment of time. So page fault rate will be decreased. This is called as working set model. And next, one more point what you need to understand is why thrashing occur. So this is the reason for thrashing. So D means demand. Demand means working set. Sum of working set means total number of demand frames. What are the demanded frames here? The demanded frames, demanded pages here is 1, 2, 5, 6, 7. What are the demanded pages here at time 2? 3, 4. What are the demanded pages at time 3? 1, 2, 3, 4, right? Based upon the demand, you need to allocate the frames to the process. That means all the time demand need to be greater than the frames. If sorry, less than the frames. For example, you need to keep the working set is 1 2 4 5 6 7. These pages need to be there in the main memory. So 1 2 3 4 5 6 total number of pages you need to keep into the main memory are 6, but you are allocating only 4 frames to that particular process. Okay, in those 6 only you can keep only 4 frames. That means you require 6. The demand is 6, but the free frames are only 4. That means M available frames are only 4. That means 6 is greater than 4. That means demand is more than the availability of a frame. D is more than available memory frames, right? That is the reason why page fault occur. So thrashing occurs. So in order to avoid thrashing, what we need to do? All the time you need to check the demand need to be less than the main memory frames. For example, the demand is 4. The memory frames are 6. So in the 6 frames, you can keep 4 pages, right? So that no thrashing will not happen. For example, you require 8 pages. Demand is 8D, but you have only 6 frames. 8 is less than 6. So automatically thrashing will be there. So we can avoid thrashing based upon the working set model. Working set means this one. You need to indicate like this. Right? So this is about working set model. And next, this is the delta. Delta means, what is delta? Delta means a working set window. The window should not too small and the window should not too large. If you keep delta too small, if you keep up to this particular one, only 3 pages are there in the set, right? So if you keep working set model up to this one, it will be a problem. So what is a delta? Delta need to be small. What is a delta? Working set window. That window means here window start from here and it ended here. Here the window started here and ended here. This window size need to be less. If it is more big enough, automatically every page will come into the working set. Are you got my point? For example, these are the required pages. 2 5 4 3 2 1 0 6 7 2 3 4 2 3 4 5 6 2 7 3 2 1 4 0 2 1, right? For example, this is the working set delta. Okay, this is the window. Then what is the working set? The working set is here to here. So how many pages are there? 2 3 4 2 3 4 5 6. That means 2 3 4 5 6 is the working set. If we increase this working set window up to this one, what is the working set then? 1 0 1 2 3 4 5 6 7. So all the pages are there in the working set. So the delta window size should not be high. It should not be high and the window size should not be low. If it is low, what happened? If it is like this only, what happened? Only in the working set you have only one page. Immediately require 4. Immediately require 0. So again the page faults will be more. So it should not be low and it should not be high. Okay. This window size at a time t1. This is a working set, right? And the next one, page fault frequency scheme. What is a page fault frequency scheme? So based upon the process page fault ratio, you need to assign the number of frames. Based upon the page fault rate for a process, you need to allocate the frames. For example, this is the page fault rate, the number of process. Some process page fault rate is up to this one. This is the lower bound. For some process, the page fault rate is high. This is higher bound. Right? For if what we need to do, page fault rate is high means the process require more number of frames. If we give more number of frames, automatically the page fault rate will be reduced. For me, that means what you need to do, this is the graph. What it indicates, by observing this one, some of the process are under the lower bound and some of the process are above the upper bound. This means lower, not lower, upper bound. Some of the process are below the lower bound and some of the process are above the upper bound, right? So what you need to do, whatever the process are above the upper bound, for them you need to provide more number of frames. Why? Because the page fault rate is more for this process. For that purpose, you need to allocate more number of frames to it, right? To them. So whenever some of the process page fault rate is under the lower bound. Whenever it is under the lower bound, what you need to do? You need to reduce the number of frames. You need to reduce the number of frames allocated to that particular process. Why? Because already their page fault rate is below the lower bound. That means that already they have enough pages in the main memory. Because of that reason, for the particular process, the page fault rate is low. If the page fault rate is low means there is no requirement of a frame for that particular process, so that we can reduce the frames from the process. We can take out the frames from the process and we can allocate them to the process which require the more frames. Okay, that is the thing. Here we are dividing the total number of process into two categories. The whose page fault rate is above the upper bound and whose page fault rate is below the page fault, below the page fault, below the lower bound. Upper bound, above the upper bound process, below the lower bound process. The process which are above the upper bound, we need to give more frames. The process which are under the below lower bound, we need to reduce the frames. That is the thing. Okay. That is the thing. Here it is not process, sorry. That is the thing. Are you got my point? If the page fault rate is more, for that particular process, you need to give more number of frames. Right? This is the end of the topic. Do you have any doubts? Do you have any doubts? Let me know. Otherwise, you need to move to the next concept.